Hola a todos. My name is Zheng Li. I'm from the University of Concepcion, Chile. On behalf of my colleagues, I would like to present our work when edge computing meets compact data structures. Our paper received quite a few interesting and very inspiring comments. So today, personally, I would like to try a different way of making presentation by giving responses to a set of selected comments, okay? Because I believe the comments perfectly drives, some of the comments perfectly drive our work logic. So I start from the motivation, all right? As we know, the latency matters in the whole edge cloud ecosystem. Even a very trivial drop of the 20 milliseconds of network latency may have very clear impacts on the loading time of web pages. And Microsoft even claimed that a half-second network delay will make them lose money. Not to mention the mission-critical applications that may have even more strict latency requirements, all right? So edge computing emerged as a very promising computing paradigm to fit in this situation. And people even argue that by combining 5G technologies together with edge computing, we can expect zero latency. But people also admit that this is still very far from the current reality, even in the near future. Okay, so minimizing the latency is still quite a valuable and important topic in the edge computing domain. And I believe we can think about this research topic in roughly two scenarios. The first one is related to the so-called narrow data processing that is also related to the typically associated with the end-to-end data communication. No matter it's from one device to another or from the device to the cloud. Especially for the later case, you see the 5G doesn't really help much. So even if we cannot reduce the absolute latency, in this case, we can try to find ways to improve the communication efficiency. For example, inspired by the internet protocols, we can develop buffer-aided communication mechanisms at the application level, or we can apply the data compression technologies to reduce the size of the data to be transferred, okay? Another scenario is the so-called wide range data processing that might involve data shuffling, because data shuffling is a quite typical component in the modern data processing frameworks models, like MapReduce or self-join applications. And in this case, the data shuffling can take up to 17% of the overall execution time. Now that's huge. So our proposal is to try to apply the compact data structure techniques to fit in this situation. To at least relieve the overhead of communication for during the data shuffling stage, okay? A very interesting comment we received is that using compact data structures is still essentially data compression. It's very interesting because I used to think the same, right? But after learning from my colleagues, I eventually realized, well, the compact data structures are not data compression. We can have a quick comparison between these two technology lines. Say we have original data. By following the technology line of data compression, well, we have a data compressor, sometimes we call it data encoder, to obtain the compressed data. Then we can have use a decompressor or decoder to recover the data to its original form to use. Or we can follow if we follow the technology line of compact data structures, well, similarly, we need a converter, or sometimes we also call it as an encoder, to get compact data. But very specifically, we let's say this community, okay, emphasize the compact data comes with the space-efficient data structures. And usually each specific space-efficient data structure also comes with, actually has to come with special operation algorithms. So all of this structure and the algorithms together will make the compact data to be able to be accessed, utilized, and analyzed directly without decompression at all. So this becomes a very attractive feature for us to address or at least relieve the previous data shuffling pressure. By the way, in this case, actually, if we need to or if we want to, we can still bring the compact data back into its original form. But usually, following this technology line, we don't have to. Or we make this at the very, very end user side. Okay. Let's use a concrete demo to see what's going on here. To facilitate applying the CDS techniques, firstly, we propose a 3-tier architecture. To facilitate the CDS application, we can imagine we just supplement a CDS layer in front of the data analytics layer, all right? And the testbed, we particularly employed Arduino Yun version 2 to represent the typical IoT or edge devices because it's not powerful at all, and it's not that so weak. We can still do something on it. Okay. As for the data sets, we employed Amazon's spot price history like this. Firstly, it's very convenient for us. It's very handy in our hands, and it perfectly matches the MapReduce workflow. You see, the price records of hundreds of service tabs, spot service tabs, are mixed together in this case. And each service tab is determined by, say, the last 3 columns, the instance tab, the operating systems, and its geographic location zone. Right? So we can directly use the original data to, we can directly use the MapReduce framework to deal with this original data, for example, to simply count how many records for each service tab, to calculate average price, to obtain the price range, the standard deviation of the price fluctuations, and the other statistical indicators of each service tab. Okay, it's doable. We have done this already. Or alternatively, we can use CDS techniques. For example, the most straightforward one, we use a predefined dictionary based on our prior knowledge because there are a fixed amount of service tabs. Then we can convert it into a much more compact form like this. Especially we can focus on the last column. We convert the service tab into a 6-digit code. Okay, by the way, this is just to facilitate the demonstration. So this code is still human readable. In practice, the formal CDS technique will use the compact data structure bit vector to convert this, say, code into at the bit level. Okay, make it only machine readable instead of human readable. But anyway, and also, there will be bit operation algorithms. But anyway, the meaning is the same. Okay, we use a much more compact code to replace the original service tabs. A natural language describe the service tabs. And the MapReduce framework doesn't have to know it's a code or it's a natural language described tab. Okay, as long as there's a key, it will work following the predefined data processing logic to count how many records, to calculate the average price, to identify the price range of each service tab. So still do the same. So in this way, we can imagine we can largely save the communication, reduce our communication overhead in the data shuffling stage of the MapReduce workflow. And we may potentially reduce the computation overhead as well. Okay, really depends on the, it'll depend on the data processing logic then. All right, and also considering, usually the network module is the most energy consuming component in mobile devices, including, for example, our cell phones. So we claim that another major benefit CDS techniques will bring to edge computing is that it might be able to help extend the battery life of IoT or edge devices if those devices have to be powered by batteries. The following question is why? Why do we need data shuffling at edge side? It's really a good question, actually. And we choose data shuffling just because it's a very typical scenario for us to justify the value to demonstrate, okay, the workflow as well, to justify the value of CDS techniques. We admit that data shuffling is not representative enough for edge computing, okay? But we believe that as long as there are needs of exchanging intermediate results across multiple IoT or edge devices, supplementing such a CDS layer will still have a chance at least to pay off, okay? And in that case, we also admit that we really need to have extensive collaboration between these two communities to identify what CDS techniques are suitable for what applications. We will need to characterize, maybe different CDS techniques will be suitable only when, the applicability of different CDS techniques will depend on the application type and also workloads characteristics. And don't forget that even in the CDS community, the various CDS techniques also have their different and dedicated application scenarios. And personally speaking, I really thought about, I don't think all of these techniques will be suitable for edge computing. So we really need to collaborate and to work together to identify suitable techniques in suitable scenarios. And even if we identified suitable techniques, CDS techniques, there's no free lunch. For example, the construction of CDS, the compact data structure, can still be space hungry. Actually, in many cases, it's still space hungry. Another major problem is that, a bigger problem, in my opinion, is that the available CDS libraries and tools are not edge computing friendly enough. They could still be too heavy, at least for the Arduino level devices. Okay, so we need to work on this. A possible way is that, for example, we don't really have to load because it's a disadvantage of the current CDS library. It's all in one piece. We don't have to load such a big library. We can separate it and only migrate the suitable functions. Another challenge is that the dynamic CDS construction. For example, what if we didn't have the prior knowledge to define to predefine a dictionary? Okay, what if we need analyze the incoming data to gradually define such a dictionary and in turn to use it to convert the original data into the CDS formatted, the compacted format data. So in this case, the computational complexity will be increased. And also considering the distributed edge computing environments, the distributed CDS constructions will potentially have inconsistency issues. And to our best knowledge, this hasn't been well studied yet, even in the CDS community. A very inspiring question, actually, and not just for the final challenge, is that why it's not well studied yet. I don't know, actually. To be honest, I was surprised when we explored the related work. For example, in the edge computing community, there are indeed papers mentioning that, well, CDS techniques will be beneficial for edge computing. But that's it. Just one sentence or two. There's no sort of comprehensive discussion, not to mention any empirical case studies. And in the CDS community, well, at least according to my literature review, the researchers mainly focus on the large amount of centralized, immediately available, and static data. Let's say, for example, in the in the bioinformatics domain. Very little work. I haven't seen any. Maybe there are, but I haven't seen any work focusing on the unique characteristics of edge computing IoT. So my assumption is, our assumption is that there's a gap. There's a big gap between these two communities. And we conclude that we really need to strengthen the collaboration between these two communities, because we believe the researchers from these two communities might not be very much aware of each other yet, because we need to strengthen our collaboration, because CDS is such a promising technology line that can benefit edge computing. Although there are still big challenges, those challenges might also be big opportunities for us. Okay, so I think this is a very good opportunity, and the co-authors encouraged me to give the presentation because I belong to our community, and it's good opportunity for us to enlarge our collaboration scope. Okay, please talk to us, especially the other two co-authors, my colleagues, who are experts in the CDS domain. Okay, so let's speed up the research. Let's explore more research opportunities on this exciting topic. Okay, muchas gracias. I'm ready to take questions.